generating function and integral representation of harmonic number comes to rescue. So here we have this infinite sum of nth harmonic number by n squared, right? I guess you guys know what nth harmonic number means, right? That's just 1 plus 1 over 2 plus 1 over 3 up to 1 over n, right? And you guys also need to know this integral representation of harmonic number, which you can easily verify that it's integral from 0 to 1 of 1 minus x to the power n by 1 minus x dx, right? And then also you guys need to know the the generating function, which is also easy to prove actually. Sum from n equals to 1 to infinity of h n x to the power n. Like how you should proceed to find this is basically write this nth harmonic number as a sum and interchange the sum and evaluate it, and you will get the expression to be minus ln of 1 minus x by 1 minus x dx. Yeah. Okay, so now that you guys are aware of that these things exist, so to find the sum from n equals to 1 to infinity of hn by n whole square, what you're gonna do is you're gonna write one of this hn by n as integral, right, and another using the generating function, and another using like generating function. So you're gonna use both of these things so that and like it will simplify. So let's see. Okay, so okay, so then let's first find these two expressions. Okay, to find the integral for h n by n, you can use the same integral, right? The same thing. And then now, if you are actually, you can actually use integration by parts in a clever way to get the expression for h n by n. So how you can do that is, okay, you can use integration by parts with this as your u and 1 over 1 minus x as b. So that will give you 1 minus x to the power n as it is, and then log of 1 minus x by minus 1, right? From 0 to 1, and then minus integral from 0 to 1. Derivative of 1 minus x to the power n is minus n x to the power n minus 1, and then ln of 1 minus x by minus 1 dx. Now minus 1 cancels out. So now over here, at x equals to 1, this 1 minus 1 becomes 0. Over here also 1 minus 1 is 0. But it turns out like this is like now 0 times infinity, right? But if you take the limit, you will actually get the 0. Minus, like because 0 times infinity is indeterminate, so you need to take limits, right? So that's what you do, and then you get 0. And similarly at 0, over here 1 minus 0 is 1. And over here ln of 1 minus 0 is 1, right? So ln of 1 is there, which is 0. So therefore again this is also 0. So over here now, notice that there's this minus n now, integral from 0 to 1, and then x to the power n minus 1 ln of 1 minus x dx, right? So now you see that okay, this hn by n is negative of this integral from 0 to 1 of x to the power n minus 1 ln of 1 minus x dx, and that is actually the integral representation for hn by n. And now similarly to find, okay, now let's just circle this little derivation, and now let's proceed towards finding the generating function for s n by n, so that we are finally ready to attack our original sum over here. Yeah. Okay. So now our generating function for s n x to the power n was this thing, right? Sum from n equals to 1 to infinity of h n x to the power n is minus ln of 1 minus x by 1 minus x, right? Yeah, and if I'm writing dx over here, I'm sorry. Okay, and now, first of all, let's make this and as an x to the power n minus 1, right? And so that there's this 1 x over here, which I will take it to the other side and divide. So I get x times 1 minus x, right? Now if I integrate both sides, let me write it as function of t for now. And there's a reason for that. T, t, t. And now if I integrate both the sides from 0 to x, I can actually take the integral inside the sum, right? And if the integral is in terms is like for t, this hn is just constant, so I can also take that out. And now over here, this becomes integral from 0 to x of minus ln of 1 minus t by d 1 minus t dt, right? Okay. Now, uh, on the left side, I have sum from n equals to 1 to infinity as n and then c t to the power n over n from 0 to x, right? On the other side, I'm first gonna break this 1 over t1 minus t as the partial fractions, which is 1 plus t by 1 over minus t, which you can easily verify. And then now over here on the other side, this is now n equals to 1 to infinity as n x to the power n by n minus 0, right? And on the other side, you will have now minus integral from, okay, this is like the integral from 0 to x of minus ln of 1 minus t by t dt. And then again, minus integral from 0 to x of ln of 1 minus t by 1 minus t dt, right? Now, left hand side is the sum from n equals to 1 to infinity as n by n x to the power n. And the other side, notice that this is just the definition of the Li2 function, right? So this is Li2 of x. And over here again, if you make use substitution that u is ln of 1 minus t, then du is just 1 by 1 minus t with minus sign. So this is just ln square 1 minus t by 2, right? Yeah. So now we have finally achieved the generating function for Hn by n. Yeah. Okay, now since we have these two tools in hand, let me also write this other formula just besides here. Okay, the other formula we have is Hn by n is equals to minus integral from 0 to 1 x to the power n minus 1 ln of 1 minus x dx. Okay, so now we have these two formulas. I think we are good to attack our original integral. Yeah. Okay, original sum actually. Okay, our original sum was sum from n equals to 1 to infinity of hn by n whole square, right? Okay, now I can write this as sum from n equals to 1 to infinity hn by n and integral for the one of the hn by n, which is okay minus n over here, integral from 0 to 1 x to the power n minus 1 ln of 1 minus x dx, right? Now I can actually interchange sum and integral 0 to 1, and then I can actually write this as ln of 1 minus x with 1 of the x over here, and then sum from n equals to 1 to infinity of hn over n x to the power n, right? And then after this, there is also dx over here. Okay, so now this is minus integral from 0 to x, ln of 1 minus x by x. We already know that this generating function is li2 of x plus ln square 1 minus t by 2. Sorry. Okay, this should be x actually. Okay, sorry, I made a okay there. Okay, over here this should have been from 0 to x, and then this would be li2 of x plus ln square 1 minus x by 2, and then at 0 it says 0, so I should have written that. I'm sorry for that. So again, here also this becomes x then, right? Okay, and now after this, what you can do is you can I can write this as minus ln of 1 minus x by x li2 of x dx plus, okay, sorry, minus integral from 0 to 1 ln cube of 1 minus x by x dx with 1 over 2 in front, right? Now for the first one, if I make substitution that u is li2 of x, du is just minus ln 1 minus x by x, right? So this is actually li2 of x whole square by 2 from 0 to 1, and minus 1 over 2. If I use reflection formula over here, this becomes ln cube x by 1 minus x. And the reason I'm doing this is now I can simplify 1 by 1 minus x using geometric series, and then you can use gamma function. So that's the reason I'm doing this. So li2 of 1 square by 2, and at 0 this is just 0 because li2 of 0 is 0, right? And then on the other side, now if I use the infinite series, this becomes sum from n equals to 0 to infinity of x to the power n, right? And this can be easily done using gamma function now. So over here, this is zeta of 2 whole square by 2 minus 1 over 2. Now the sum from n equals to 0 to infinity. An integral from 0 to 1 of ln cube x to the power n dx. How will you do that? Okay, so that will basically be just minus 1 to the power 3 gamma of 3 plus 1 by n plus 1 to the power 3 plus 1. So this is the formula. So whatever is the power of ln, that will be the power of negative 1, and then gamma of the power of ln plus 1, and then again power of x plus 1 to the power of ln plus 1, right? So that's the formula. And now this is pi square by 72, and you can easily verify this formula using use of substitution that u is ln x, and then you will just use the normal formulas. And now this becomes plus sum from n equals to 0 to infinity. Now this is a 3 factorial, which is 6, but this is n plus 1 to the power 4, right? Now this is pi square to the power 70. Wait, this is pi to the power 4 actually. I'm sorry. Pi to the power 4. Pi to the, because zeta of 2 is pi square by 6, right? Yeah. And then over here, this is just 3 times, now this is zeta of 4, which is pi to the power 4 by 90. Now if I take the LCM, LCM will be 360 pi to the power 4 times 5, right? And then 30 times 12, right? So this is 17 pi to the power 4 by 360. That's the answer. 17 pi to the power 360. But the interesting thing is, like, who would have thought, like, that the sum of the reciprocal of, like, the natural numbers divided by n and then squared, this could sum up to pi? Like, isn't this interesting? How in this reciprocated infinite series, this pi always shows up? There's also a video by 3 Blue 1 Brown explaining this, but yeah, like, this is pretty interesting how in all the reciprocal sums, there is definitely some pi in some form, and that's quite fascinating, guys. And what all we can do is be fascinated and try to explore things. Yeah, this one. Okay, so the moral of this story is you can actually use the integral and the generating function of harmonic number to find other integral and harmonic numbers, and you can use that to solve problems like we did over here. And definitely we need some polylogarithms and things like that. But overall, it nicely folded out to be 17 pi to the power of 360. I hope you guys enjoyed this problem, and definitely apply these techniques in other like problems too. I hope you enjoyed the video, and I look forward to seeing you in the upcoming videos too.